Let's look at a very quick example of pseudo-random number generation with inverse CDF. So I have a couple of modules on this subject, but here I'm going to focus purely on intuition. The method using the inverse CDF can be used to generate so-called pseudo-random number sequences. And when we say pseudo, because we want to emphasize that these are generated inside the computer and they're not truly random. Because this method is based on having the uniform random numbers, and uniform random numbers are usually generated by a computer in a deterministic sequence, but this sequence will look very much like a random number sequence. So it's pretty much, for all intents and purposes, indistinguishable from a truly random number sequence, the uniform random number. Then we plug it into the inverse CDF and obtain the random number from a different, not uniform distribution. So that's the method I'm going to discuss here. Again, the theory part, quote unquote, comes from Wikipedia. I give you the link. Take a look at it, read it. The idea, though, is very simple, actually. So think about this. Let's say we have probability distribution such as beta. So the beta distribution, I chose it because it's easy to deal with, but the same idea works with pretty much any continuous distribution. You can make it also work with discrete distributions too, but here I'm using it's the easiest to work with continuous distribution when we're learning the technique. Right, so here this is how beta distributions look like. It generates the numbers, or it works with numbers in that span from 0 to 1. So all the numbers in beta distribution are between 0 and 1. For instance, depending on if you are using two parameters of beta distribution, alpha equal 2 and beta equal 2, then you will get this purple line. And what purple line tells us, it's a PDF. It tells us that mostly the numbers which come from this beta distribution will be around 0.5. Right? The greatest number of beta distributed numbers will be around 0.5, and that is for this set of parameters. If we use some other set of parameters, such as maybe what is this, like a yellow orange line, that looks like yes, that looks like alpha and beta both equal to 0.5, and in this set of parameters, you see most numbers will come from around will be around 1 and 0. You see the density is highest around 0 and 1. For our test, I'm going to use this arc-shaped beta distribution with parameters alpha and beta both equal to 2. So the highest density will be around 0.5. Now let's this was a density function, but let's build the CDF, a cumulative distribution function. So for this set of parameters, CDF is going to look like the purple line again. So what's interesting about CDF is that, as you know, or you should know, the CDF is always from 0 to 1. And not only that, but CDF is also monotonically non-decreasing or increasing function, let's say, right? So it always starts at 0 and always ends at 1. CDF, cumulative distribution function, unlike the density, which can have all kinds of shapes. CDF always starts from 0, always comes to 1, never goes down. It may be flat, but it never goes down. So its slope is always either upward or flat. So it can be quite flat and then, let's say, quickly increases, right, for some set of parameters, or it could be quickly increasing and then becomes flat. But in any case, never ever it goes down. And that means that it has a unique one-to-one relationship between your random between its parameter x and parameter y. It's one-to-one. So if you know y, you can always find x, right? So you take any y, right? Let's say what is it, 0.6, and then you find wherever it intersects with that CDF of yours, you can always find what is corresponding x. And the same way, if you know x, that's why. Why is it working that way? Well, because by definition, what is a CDF, cumulative distribution function? CDF is the probability that your random number is lesser or equal to certain number, which is your number on x-axis. So for instance, at 0.8, your CDF means that what is the probability that the beta distribution with these parameters, what is the probability that the beta distributed number will be less than or equal to 0.8? And just by construction, it is always monotonically increasing, right? So there's one-to-one relationship, which gives us an interesting idea or an interesting observation. If we take a random sample and then plug it into the CDF, and that's what this Wikipedia page is telling us, right? So if you take a random number and plug it into the CDF. So in this case, F is CDF. Oftentimes in statistical literature, the cumulative distribution function is denoted with big F, with capital F. So if you're plugging the random number, let's say from beta distribution, then what will happen is that on the output, CDF of that random number will be uniform distributed function, uniform 0 to 1. And again, we know that the probability distribution, CDF of the probability distribution goes from 0 to 1 always, right? So it happens so that if we're if we're inserting our random number into its own CDF, then on the output we would be getting the number from 0 to 1, and not only it's a number from 0 to 1, but it also is going to be uniform random number 0 to 1, which tells us that what if we took the uniform random number and plugged into inverse CDF, right? And then we would be getting logically the random number from that distribution. So if we take the inverse CDF of the beta distribution and plug into it the uniform numbers, we would be getting beta distributed number. Vice versa, like I just said twice, if you take the CDF, cumulative distribution function of beta distribution, and plug into it beta random variables, on the output you would be getting uniform random numbers. So the idea again is, like I said, so if your beta, if your on x-axis is beta distribution, and then you are plugging these beta into CDF, the CDF output will be on y-axis, and these would be uniform random numbers. So let's have a very quick example. So here in column B, look at the formula. I'm using the same inverse CDF approach, which I have a video on, right? So this is a beta inverse CDF, inverse cumulative distribution function of beta distribution. And I'm using these parameters. And in column B, I generated these beta distributed random numbers. Now I'm taking these random numbers, obviously, if I run them, and I'm going to look at the following. So I'm looking at just one number, the very first one. Doesn't matter, I could pick any number, but I'm looking at the very first random number and plugging it into the CDF. And then I'm drawing the CDF here. Look, so if I press F9 several times, what you need to be observing is the following. When I'm pressing F9, I'm generating the new random number, right? So what I'm showing here is that, well, Okay, I pressed F9. What was the number? 0.58, right? So I am showing you this 0.58 on x-axis. So this is your beta distributed random number. And then if I plug it into, and then if I draw the CDF of beta distribution, then the CDF of 0.58 is on y-axis. Right, so if I were writing down these numbers here on y-axis, the CDF of the beta distributed number, then I would have noticed that obviously you can't prove it visually, right? But what's going on is you see that when we're plugging the random number in x-axis into CDF and then recording the numbers on y, we will see that y is also a random number. And you have to believe me here, but y is from uniform distribution. Right, so when we're generating random numbers, each random on x will correspond, obviously, or will produce the random number on y, which tells us that maybe we can inverse it. And I can tell you, yes, we can inverse. So now imagine, forget that we are generating x and then reading the y. Imagine that actually we are generating uniform random numbers on y and then applying inverse CDF to get x. So imagine that this was the input, right? Random, uniform random numbers, plugging into inverse CDF and getting x. So this was input, this is output. Right? So because this function CDF is there's always an inverse. It's one-to-one relationship between x and y. Because of that, we are able to generate uniform random numbers, plug them into inverse CDF, and get let's say beta distributed numbers on the output. That's the intuition of this inverse CDF method. And where is it used? It can be used to actually generate random numbers, but I alluded to it earlier. I said in the random number Excel video of random number generation videos, modules, I said that it may not be the most efficient method, and it's true. It's sort of slow, like unless your inverse CDF is very fast, and it happens so in a lot of cases in many interesting probability distributions, that inverse CDF is not easy to calculate. Sometimes it is easy, but oftentimes it's not. Even in case of normal distribution, it's not that easy, right? It's slow function. So this method, inverse CDF, may not be the best one for you to use. But it does work. But the most common, or I would say the common use of this technique in my lectures will be in generating correlated random numbers with copulas. So the copulas are this technique which helps to generate correlated uniform random numbers. So the copula generates uniform random numbers. Now, if we take these uniform random numbers and plug them into the inverse CDF of your interest, then you will get correlated non-uniform random numbers. So you can generate all kinds of very interesting joint probability distributions. So that is how I'm going to be using this in my advanced econometrics course.